Hello everyone and welcome to my talk at SNIA's Storage Developer Conference. Today, we shall discuss some challenges and opportunities with hyperscale boot drives. My name is Karthik Shivram and I'm a storage engineer within Facebook's infrastructure team. Here's a brief agenda of my talk. I'll start off with a bit of introduction about this topic and then go into details on some of the options we have to boot a server in a hyperscale setting, and finally discuss some of the challenges associated when SSDs are selected as a boot drive option, and finally propose a solution for all of these challenges. Facebook has a massive scale in terms of its infrastructure in order to serve billions of people and to support its wide range of products all over the world. All of this is tied by a common goal within the infrastructure organization, which is to build the most innovative and highly efficient data centers on Earth. These data centers are present all across the globe. Specifically, Facebook operates around 17 data centers, and what this means for the sake of this talk is that Facebook deploys boot drives all over the world. I'll come back to why this is an important topic and how it generates unique requirements in a hyperscale environment. But before we get into the details, let me start off with a brief background on flash drives in a hyperscale data center. Hyperscalers deploy two types of SSDs, data drives and boot drives. Data drives are typically used for data storage applications such as databases and cache, where low latencies are desired. And they're also usually larger in capacity, roughly in the range of 2 to 8 terabytes. They operate with a larger power budget, anywhere from 8.5 watts to 20 watts, and they're found in many form factors such as E1.S, M.2, and U.2. Data drives also contain an onboard capacitance to ensure data durability during a power loss event. On the other hand, boot drives are primarily used to store the OS and, in some cases, used to store applications and service logs. It is also used as a scratchpad memory in stateless services. They're typically smaller in size, form factor wise, and the preference being M.2 22 by 80, smaller in terms of capacity, generally around 512 gigabytes or smaller, and there's usually no desire to have power loss protection. In my subsequent slides, I will delve deeper into some of these requirements and also discuss why a SSD-based boot drive is a good choice for hyperscalers. The key takeaway here is that boot drives are deployed by hyperscalers, but the requirements for this commodity is not well understood by the industry. So where do hyperscalers use boot drives? Here's a picture of a typical data center rack. As we can see here, there are some compute nodes and storage nodes, and all of these are accessed over the network through a top of the rack switch. As highlighted here, each of the servers or nodes has its own boot drive, and the reason for this becomes clear as we understand the various choices we have for booting a server in a data center. The key point I would like to make here is that in a typical data center rack, there are multiple boot drives. So what are some of the options to boot a server? Well, we can use HDDs, SSDs, or even boot off the network. Let's study these options in a bit more detail. HDDs are made of mechanical components which are less reliable than solid-state chips. And as a result of this, they have reduced reliability, which then increases operational complexity. They have poor random performance when the access patterns are random in nature. In terms of power, they're pretty power hungry and consumes greater than 5 watts typically in terms of active power. They're also available in very large capacities than what's actually needed by boot drive applications. They lack I2C or sideband access, which is typically the method of monitoring health on boot drives via a BMC in most data centers. And then they consume more space physically, which makes it challenging to accommodate an HDD in high density designs. One such example is a server on the in the picture on the right here, which is a Yosemite V3 sled contributed to OCP recently. This is made of 4 Delta Lake motherboards where the boot drive resides. To summarize this slide, HDDs are not a very suitable option to be used as a boot drive in high-density server designs. Next, let's talk about network boot. As the name suggests, this option consumes network bandwidth, which is a critical resource for most hyperscalers. Network boot increases complexity of the system and it reduces the reliability of the overall system, as a single drive failure has potential to take down multiple hosts at the same time. Furthermore, it increases the boot up time and adds additional I/O latency, which makes disaster recovery type of scenarios very challenging. In short, network boot is a great option, but it is complex and challenging to implement at scale, and it introduces many risks into the data center infrastructure reliability. Next, let's talk about SSDs. As mentioned previously, there are typically two main types of drives: enterprise SSDs and client SSDs. And both of these are made of non-movable components or semiconductor components, and they offer great random workload performance. Specifically, client SSDs are capable of supporting many of the hyperscale needs, such as low active and idle power, security features such as secure boot, and they have increased reliability as they don't have any moving parts. In terms of blast radius, they're also much better since we can connect a drive into every system within the rack. They're also available in smaller form factors, which makes it easy to integrate within a high density server design. And they're also widely available, which is also an important factor when we are talking about hyperscale deployment. So client SSDs are more aligned to hyperscale boot drive requirements, but they do come with some challenges. Let's study some of the challenges associated with client SSDs. Here's a chart that shows the average capacity trends for data drives in hyperscale in the next 5 years. As we can see here, the average capacity ranges anywhere between 2 terabytes in 2020 and goes all the way up to 6 terabytes in 2025. Boot drives, on the other hand, do not follow the same trend. In fact, they remain pretty much a constant. Boot drives remain at 512 gigabytes or even smaller in the next few years. So increasing capacity and following this trend for boot drives would lead to increasing expenses, which is not very desirable. This point is further evident in this chart, which shows a typical boot drive utilization based on 256 gigabyte boot SSD. As we can see here, the total disk utilization for a boot drive remains pretty low, and it's roughly around 50% of the boot drive capacity. The rest of it is occupied by the operating system, swap if it's enabled on the system logs, application logs, and in some compute applications, the device is also used as scratchpad region to store temporary results during computations. Client SSDs are a great option here as they're generally widely available. However, they're designed with a different mindset. Let's study that in a bit more detail. This slide here talks about the differences between client and hyperscale environment. Most client SSDs are designed typically around a laptop use case. So when we use this device as is in a hyperscale, it creates lots of challenges. Some of the metrics such as idle time and power saving, which are very critical from a client use case because we need to save the battery, are pretty much not important. Idle time is very challenging to be found in a hyperscale environment, as the disk is always seeing some amount of I/O. And client SSDs typically care about fresh out of box performance, whereas hyperscalers mostly care about sustained performance. Additionally, security, monitoring, and endurance are not that critical for client usage. However, these are all very important features for hyperscalers. Let's study a hyperscale boot drive I/O profile to better understand these requirements. Here's an example chart that shows a boot drive I/O profile taken from a boot drive application. As we can see here, the drive is constantly under I/O stress. It sees all types of traffic, reads, writes, and trims all the time. It's worth to note that the trim rate is especially high on boot drives, mainly because of the nature of the workload that the boot drive sees. There are constantly files being generated and deleted, which results in a high trim rate. And latency stalls due to trims are not very desirable since it leads to poor application performance. Double-clicking on this I/O profile, the chart on the left shows the constitution of this workload. It shows that the workload is mostly made of random traffic and primarily random writes and random reads, which for a flash drive means that we'll have an increased background activity as a result of an increased write amplification. The chart on the right shows the queue depth on these workloads. Most boot drive workloads are low in terms of queue depth, but they're also very sensitive to latency stalls, as it leads to poor user experience. Talking about performance and workloads, I would like to highlight that there's a lack of industry standard or benchmark to characterize a hyperscale boot drive use case. This leads to hyperscalers dealing with huge variation in drive performance, which is again not very desirable as it leads to inefficiencies. Lastly, as I mentioned earlier, these SSDs are deployed across various data centers around the world. So tracking health and monitoring these parameters are extremely important. Additionally, getting more health metrics from a device helps with failure prediction and detection. Monitoring is also needed to track the life remaining in terms of endurance for an SSD. And hyperscaler desires high amounts of endurance to prevent early wear out. As previously mentioned, repairing at hyperscale is very challenging. So lack of industry standard makes it very challenging for SSD makers to understand what type of endurance is needed by hyperscalers. So to summarize, here's a recap of all the challenges that are present with a boot drive solution based on client SSDs. Capacity of SSDs are increasing, however the boot drive capacity remains constant. Client SSDs are capable of supporting hyperscale needs, but they are designed with a client use case in mind. Most of the hyperscalers have confidential specifications which are given out to the vendors to customize these use cases. And hyperscalers require highly secure, higher endurance, and enhanced monitoring compared to client SSDs. And as I mentioned, hyperscalers have confidential boot SSD specifications, which doesn't really encourage industry collaboration. So how do we solve some of these challenges? Facebook and Google are collaborating and combining requirements to create a hyperscale boot SSD specification. This spec will be openly available to everybody and will be contributed to OCP. A combined SSD boot drive requirement is a single document that comprises of all the requirements that hyperscalers desire from a boot drive. It allows the market to understand what features hyperscalers need to manage boot SSDs at scale. It also allows the market to understand and use the SSD that hyperscalers use. Further, it reduces SSD market fragmentation and encourages the use of open source tools such as NVMe CLI to manage and monitor these devices at scale. Finally, it helps third-party test vendors to create compliance suites which will further help in reducing the qualification time. In short, the opening requirements helps increase industry collaboration and it reduces SSD market fragmentation. So what's comprised in such a spec? The key focus of the spec is to contain all the requirements that are needed to build and manage a hyperscale boot SSD. This includes clearly specifying mandatory and optional requirements that are needed to be supported around NVMe Express and PCI Express. As usually in these documents, there are lots of optional features and oftentimes it becomes challenging to understand what needs to be supported for hyperscale use case. It also contains an exhaustive list of extended smart metrics for enhanced monitoring. It contains reliability requirements with endurance targets, thermal requirements, and power budgets which will help in integrating these drives into hyperscale servers, performance targets which are based on open source benchmarks, and most importantly, specifying the performance measurement methodologies. It also contains security-related requirements, which is a very important feature for hyperscalers, and contains requirements around monitoring and tooling, including requirements around sideband and SMBus. So in short, it contains and specs out everything that's needed to build a hyperscale boot SSD. In conclusion, here's my vision and roadmap to a brighter future that solves all those challenges in the area of hyperscale boot SSDs highlighted previously in this talk. Today, boot drives are being customized by vendors, but there's a lack of industry standard which hinders collaboration. OCP hyperscale boot drive specification will solve these challenges as it will not only benefit system makers but will also benefit SSD providers and it will promote additional collaboration between hyperscalers and the industry. With that note, I'd like to conclude my talk and I would like to thank you all for attending this presentation. Thank you once again.